Hello everyone, and welcome to this afternoon's IMechE talk, Achieving Bolted Joint Integrity Through Load Measurement. My name is Matthew Hudson. I'm a representative from the South Lancashire Young Members Panel who have organised this talk, and I'll be your host and moderator. Presenting to us today, we have Craig, a product manager from James Walker who produce the RotaBolt product. If any of you have any questions throughout the presentation, please put them in the chat section, which is indicated by the speech bubble button, and Craig will answer as many as he can in the Q&A after the presentation. Please note that everyone can see the message section, that's both our speaker, myself, and the attendees. And if everyone can just ensure that your camera is switched off. If you can see your face somewhere, so can we. So just make sure that the camera icon has a line through it. This presentation is being recorded along with the Q&A afterwards, so if you'd like a copy of the recording, just email me afterwards and I'll make sure to get that sent out to you within the next few days. So with that, I'd like to hand over to you, Craig.
Thanks a lot, Matthew. I noticed you didn't try and pronounce my surname there, so good job on that. So I'm Craig Gingell. I'm the product manager for the RotaBolt product within the James Walker group. So what I'm going to do today is a quick introduction, because we've only got a limited amount of time. So we're going to introduce the idea of bolted joint integrity, what's involved, how is it achieved, why do we want it, and first thing I'm going to do is turn my camera off, because my screen is in another direction and I don't want you looking at the side of my head for the entire time. So I'll just switch that off and we'll crack on. We will crack on when my computer decides to move to the next page. There we go. So first up, copyright notice. I have to show that. Don't bother reading it yet. Just some disclaimer notices. So what we're going to do today, we're going to look at the basics and the terminology. We're going to look at why is bolt loading important, how you currently monitor bolt loads, methods for tightening them and how you achieve those loads in the first place, ways in which things can go wrong for failure modes, and then at the end I'm going to do a quick recap of the RotaBolt specific products. So up until that point, everything I do is going to be generic to the marketplace and the technology rather than my RotaBolt product. So let's start really basic. What is a bolt? And this is something that I have to apologize at the first start. Fasteners is the collective term, whether you've got the hex-headed bolt or the all-thread stud or a double-ended stud. The term is fasteners. I often say bolt, so I apologize that I will probably refer to everything as a bolt throughout the rest of this talk. But that is something that you hear often in industry as well, so I don't feel too guilty about that. So let's keep it basic. What is a bolt? Or I've done it already. In this case, there's a picture of a stud on the screen. So we have to remember that going back to very, very basics, we're talking about a very stiff spring. The bolt has mechanical properties, as with any metallic, any spring. You have an elastic region, you have a yield point, and you have then into plastic region and failure. So as long as you stay within the elastic region of the material, you stretch it and it will return to its original dimensions. So the bolts are then interacting with a flange of some description. And we've got a similar thing there. The metallic materials of that flange will act as a very, very stiff spring. But at this point, we're compressing them. We're not in tension. And when you put those two together, you've got a tension spring inside a compression spring. Now, it's important to remember that, because even though we can't see it, when you are tightening these bolted joints, there's quite a lot of movement on the microscopic level. A couple of micron stretch here and there can make quite a big bit of difference. So there is physical movement, even though we might not necessarily be able to see it ourselves. So we'll look at that then as we've looked at a little bit of the bolts and the stud. So we're going to look at the joint as a whole. So how do you get a good bolted joint? And there's three pillars. I know there's more to it than this, but we're going to simplify it down to three basic points. You have the design of the joint, the component quality, and the installation. So when you consider the joint design, you have lots of international standards that you have to comply with, ISO standards, ASME standards. You'll have some sort of computing software that's helping you do all that. So as a general rule, the design is taken, you will almost assume it as being correct. And a similar thing then with the component quality. So you have material certification, you have testing, you have all sorts of things you can do to confirm that the material and the quality of the component that you have is correct for the application. And then when you come on to installation, it tends to all fall down because there's not really that control element to it. You have torque wrenches and calibrated pieces of equipment, but they don't actually measure what you're intending to achieve. And that is really the point of this talk today. So the bolted joint is only as good as its weakest link. Having good design and good component quality is useless if you have poor installation. And why is that? Well, again, coming back right to basics, but let's work backwards because no one cares about bolts. The bolt is a means to an end to achieve something. What is that? So what do I want? I want a safe joint and I want long-term integrity. I want to fit and forget. I want it to be there. I want it to work. If I've got a pressure containing vessel or some sort of fluid running through a pipeline, I don't want to lose any product. I don't want to have the downtime to maintain it. I don't have to constantly retighten things. And obviously, above all, you want its safety. And then, depending on which currency you're in, you want to save money as well. So that is the ultimate aim throughout all of this. We want whatever plant that you're running on or whatever piece of equipment you've got, you want it just to work reliably. So how do you go about doing it? So if you look at the drawing of the flange in the top right hand corner of the screen, firstly, you have a working force acting on that joint, trying to pull it apart. And the analogy I use sometimes is a piece of paper. If you get two pieces of paper and place them together and let go, they'll come apart. Be it gravity or wind or whatever, some form of force is working on that to pull that joint apart. So we need a paper clip, or in our case, some bolts. We need to create a clamp load that's sufficient to overcome those working forces. So very basic physics, Newton's laws. We need the force in one direction to be counteracted by the force in the other direction. Now we have to be a little bit careful in that we don't just need to be above a minimum. We need to make sure that we don't rotate flanges in the case of something like a raised face flange on a pressure vessel. We can't be crushing gaskets, and we obviously don't want to be yielding the bolts. So we have a range there that we can work within. How do we create that? Well, it's pretty obvious because it's the reason we're all here. We tighten the fastener. So again, Newton's laws. When you create the load in the fastener by turning the nut or the hex head, you're creating that stretch, and then as it tries to return to its original length, it's creating that clamp force and pulling that flange together. So you've installed it. How do you know you've done it correctly? Well, how do you know you've done anything correctly? You measure it, or you find some sort of system in checking that what you've done is correct. How does a torque wrench measure load? Some people might disagree or shout at me now. It doesn't, and we're going to have a look at that. If you look at the basic terminology, torque is a rotational force. Now, what we're trying to achieve in the bolt is a load or a tension, depending on how you want to describe it. So we want a linear axial force in that bolt or tension. So torque is a means to an end. It's not the end goal. So when we're rotating the nut, it's sliding against the threads, and the helical shape of those threads is what's then creating that stretch. But whenever you've got one surface sliding against another surface, again, back to basics, we have friction. So when you designing these bolted joints, the designer with their computer software or whatever knowledge and experience they have is going to be thinking of a friction factor, a coefficient of friction, or a nut factor, however you want to term it, of how much force it's going to take to rotate that nut to create that load. But then you get out in the real world and things don't quite go to plan. And things that can affect friction are the surface finish. That could be poorly machined parts, or it could be as simple as a bit of dirt that you hadn't wiped off. The washer type, are you using a F436 washer or an ASME PCC1 laser cut high tolerance washer? Lubrication tolerance, are you using the same lubricant that the engineer who was designing the system intended you to? How much lubrication is used? Is this your first bolt of the day? Is this your last bolt of the day? Have you put the same amount on each bolt that you're tightening in that day of work? And this thread deflection and work hardening, is this the first time that you've tightened this bolt or the 15th time that you've tightened it? All these things can affect the friction, and it doesn't take a lot of variation in the coefficient of friction to create quite a lot of load scatter in the end result. Then we're looking at the tension or load, so the stress resulting from the elongation, and people bring in hydraulic tensioners. So another tightening tool, again, I'm not trying to put anything against these tools. These are tools that you need in order to tighten the bolts, but you have to understand their application and the limitations. So with a hydraulic tensioner, we put the tool on the bolt, pressurize it, and it creates an axial load in the bolt. Now at this stage, the bolt load is equal to the pressure multiplied by the pressure area of the tool. We know what it is, it's measurable, it's good. But this is only half the tightening cycle. We now need to remove the tool. So we run the nut down, release the pressure, and the job's done. We've now got the tool off. But in transferring the load from the feet of the tool to the nut, we've now created load transfer relaxation. Now there are graphs in which involve the length to diameter ratio of the bolts to allow you to overload the bolts initially to compensate for that load transfer relaxation. But John Bickford, writer of the Introduction to the Design and Application of Bolted Joints, he's carried out some research. So 90 bolts were taken, all the same size, the same diameter, and the same material. And they were overloaded to 79% of their yield. So in theory, they should all then relax back to the same level. But as you can see from the graph, the target residual load was between 60 and 65%. The actual achieved load measured after the tool was removed, 2/3 of those bolts were outside of that initial scope. Some of them by quite a lot, some of them not so much. But there is an issue there in terms of how accurate that is going to be in terms of a residual load. It was key that we remember with the tightening methods, torque is a rotational force, tension is an axial load. With a torque wrench, you need to overcome the friction, and with a tensioner, you need to overload the bolt to compensate for relaxation. Torque wrenches can be plus or minus 30% accurate or inaccurate. I think the VDI standards, you need to use a 1.6 safety factor whenever you're designing something that you're torque tightening with. And a tensioner, we say plus or minus 20%. So that there's a room there for the load that you have in the bolt once you've walked away from it to be different to what you think it is. The key here is torque wrench does not measure load, and a hydraulic tensioner doesn't measure the residual load. And the key message within that page is just the title at the top. These are just methods of tightening. They're not methods of measuring. So how do we go about doing that? The reality is we don't measure load unless you're in a laboratory type environment or you have a load cell where you are directly measuring load. Nobody actually measures load. We use Hooke's law, which states that stress is directly proportional to the strain, and we measure the strain. Just as a reminder, strain is a comparison from the original length to its new length. That allows you to work out the stress that's in the bolt and therefore the load. So there's a couple of ways that you can do that. Basic elongation. So you measure the fastener in its rest condition and you measure it again in its fully loaded condition with some form of caliper gauge. And it's simple. You've done it. You've got the difference between its rest condition and its loaded condition. So some of the pros and cons of these, you do need to have access to both ends of the fastener in order to carry out this method. There's no bolt modifications needed, and that'll become clearer when we talk about some of the other methods. Obviously, you can't use it for a blind hole. If you're screwing a hex-headed bolt into a hole, rather than a through bolt application, you can't access the other end, and therefore you can't use this method. It can be relatively low cost and can be quite accurate. You get the installation loads, so you can measure it on installation, and then provided you've kept good records as to which bolt you're measuring and what their original lengths were, you can come back at a later date, measure it again, and get an in situ operational reading. Another way of doing it is with an electronic strain gauge. So you have, again, I've tried to create a generic description of the technology. So a wire is fixed to the fastener and then it stretches as the fastener stretches. So the Wheatstone bridge circuit, as we've shown there, is pretty much the way of doing this. And what happens is the elongation of the fastener causes the wire to stretch, which creates an electrical resistance change. And that then is measured to allow us to work out the strain and therefore the load. Now these can be very, very accurate, but then to go alongside it, they can be quite delicate and they are quite expensive. So you tend to find these more again in a laboratory type environment or maybe a research and development type installation. So you can get the installation load, so you can monitor this as you're loading it, and you can come back and monitor these while they're in operation, provided you have some sort of power supply available and the electrical wire is mounted in such a way that allows you to do that. So some don't, some do allow you to get the operational monitoring. Ultrasound, this is quite a popular method in the wind industry and other forms of heavy engineering. So here we're sending an ultrasonic pulse from the top of the head of the bolt through the central axis, and then a reflection is coming from the end of the bolt back up to the sensor. Now we know the speed of sound in that particular material, and therefore we can calculate the time of flight, which equals the extension of the bolt. So again, with this method, you do need to know what the length of the bolt was when you started, and you have to keep records of what that was. So when you come back to measure it the second time, you can compare it. They can be very accurate. As long as you know how to use the equipment and you do these properly, you can get a good reading off these. They usually have some sort of transducer fixed to the top of the parent fastener to allow the ultrasonic signal to pass through the material without any sort of distortion at the initial point. They can be expensive, depends what you're comparing it to and what you consider to be expensive, but relatively can be quite expensive. And they're most likely a removable reader. So this is the kind of thing you're going to come along, you're going to take a reading with that tool and then walk away with the tool with you. It's not something you leave in place. You do need a clean surface, and with these you can achieve installation loads, and then you can come back and, as we mentioned before, provided you've kept good records of what bolt you're measuring and what length it was at when it was installed, you can now come back and measure in situ without taking any equipment offline. Then the mechanical strain gauge. So this is where James Walker RotaBolt products come in, but I'm going to try and keep the description as technologically neutral as possible. So you have some sort of physical pin inserted into the bolt, and there's a datum point on the head of the bolt, and there's a datum point on the reader. So in the picture you see there, the reader in this case would be the sintered cap on the top, but there are removable readers and there are a number of different ways of doing that. But here there's a known gap between two datum points. And as the pin isn't loaded, so the bolt is loaded and stretches, the pin is unloaded and therefore stays the same length. So the change in that gap allows you to work out the elongation. It'll become more obvious when I look at the RotaBolt product in detail, but again, I'm trying to keep it technologically neutral at this stage. So the downside to these is you can see from the diagram there, you do need to modify the parent fastener. We do need to drill that hole down the center axis in order to fix the mechanical strain gauge pin. Now, there are some removable tools so that you can snap on some sort of reader, or you can get on bolt readings, so you just leave it in place. They're relatively low cost compared to the other methodologies we've looked at so far, and they can be quite robust. There's no wires. It's quite a heavy metallic components, so they are quite robust, and you can get installation readings and then you can get in situ operational readings to leave the reader in place. So we've talked about some of the theory. So we look at from a real world application, and I've selected offshore wind as an example. I mean, it's a big industry globally at the moment, specifically in the UK, we're world leaders. But one of the reasons I've looked at this is there's a lot of transferable applications. So heavy engineering, vibrating equipment, rotating, you have gearboxes, you have bearings, you have plain structural joints. There's all sorts of different joints within a wind turbine that has lots of applications for other industries. And one of the interesting joints to look at is the transition piece. So for anyone that's not been involved in the wind industry, you have specifically in the European North Sea area, monopile foundations are the primary way of fixing. So you have basically a big spike, for want of a better word, into the seabed. You then have a transition piece, which is often the yellow pieces you see on wind turbine diagrams, and then the turbine is bolted onto that. So these are big bits of equipment. M72 bolts are not uncommon, and as the wind turbines get bigger, we can look at M90s. So these are big bits of kit, and the bigger the bolts, the bigger the surface area, the more issues you start to get with friction variances. It tends to be a bit of an exponential build from the small bolts up to the large stuff. And it's important that you get the load distributed amongst these bolts needs to be uniform. If you don't have any sort of tension monitoring included, you have some bolts that are high, some bolts that are low, some bolts that will be about right. Then as these things start swaying or vibrating or have any sort of external forces applied, any lack of uniformity in that clamp load starts to become worse. So it's important that critical large diameter, difficult to access bolts. These are not things that you can just walk up to and retighten very easily. So it's a very critical piece of equipment that you get right at the front end. And then the bit that people don't often think about, you've got the human challenges of that. So one way of monitoring bolt loads in wind turbines at the moment is they basically, after 6 months after the initial installation, they'll come back and they'll retighten every bolt because they don't always have any tension monitoring in place. So you'll have a standard bolt. So they'll come out and retorque each and every bolt on that joint. Now, to tighten, you've got very heavy hydraulic tools. And the people tightening may have just been on a 2-hour boat ride to get there. And these are some of the issues that I've spoken to from different wind farm operators around the world who've said they have real issues with these. Yes, they're theoretical and I'm talking to you in a hypothetical way, but these are real issues that people are experiencing in the world at the moment. So drop tools, obviously from a mounting piece or a transition piece, you're at the bottom of the turbine. So it's not a good thing to happen, but it's not quite as bad as when you start messing with the nacelle, the gearbox. If you start dropping tools there's much bigger issues. Strain muscles, if you think the bolts are potentially 20-25 kilos each, and then you have the hydraulic, think of a hydraulic torque wrench, and then the cables and the power packs that come with that, there's a lot of human effort that has gone into doing these. Trap fingers, people getting their fingers trapped in a torque wrench is a real issue, bigger than we would like to think. And obviously then the sick pay and the compensation claims that come with it. So achieving your bolted joint integrity is not just a mechanical issue. It's a whole world thing. Failure modes. So what do you consider to be a joint failure? If a joint leaks, is that a failure? I think everyone would agree, yeah, that'd be considered a failure. If a bolt snaps, is that a failure? Again, I think most people would agree with that. What if you've got a perfectly functional joint, but you need to regularly retighten it to maintain the integrity? So it's never ever gone wrong, it's never leaked, nothing's ever fallen over, but you revisit it every week or 2 weeks to retighten it. Is that a failure? It depends on your interpretation, but certainly room for improvement. And these are some of the reasons why these things are happening. So self-loosening. When you have vibrating equipment, the lateral movement caused by the vibrations acts with the helical shape of the thread to try and shake the nut loose. So the nut starts to turn off, and then you've lost load in the bolt, and they can be completely, they can lose load to the point of experiencing fatigue, or they can sometimes actually wind themselves out of the joint. Mentioned fatigue there. If you have a bolt that's experienced working forces and the preload isn't sufficient over a period of time, they can start to catastrophically fail through fatigue failure. Yielding on installation is another one where, because of the load scatter of the tightening methods, you actually yield the bolt just when you're installing it. You don't ever put that piece of equipment into operation, and still you've broken the bolt before you started. Bent flanges, we mentioned on sort of pipelines, especially with raised face flanges, you need to be careful. If you've over tightened them, you could bend the flanges, and pipeline leaks. All of these can be caused by incorrect bolt tension, either too high or too low. Now, there are other things that can cause these, and there are other ways of fixing these problems. For example, a pipeline leak, you could put a leak clamp on there, but it's by far easier, cheaper, and more engineeringly correct in order to address the situation that the bolt tension is checked first. An example of where this has actually happened in Sweden, Christmas Eve 2015, one of their wind turbines collapsed. And when the report came out, there's a lot of words on there, don't worry about all of it. They showed there's clear signs of fatigue and corrosion at the joint between the bottom and second section of the tower. The bolts that held it together had suffered from a fatigue process and could no longer withstand the loads of normal operation. And the reason was the pre-tension force in the joint was too low. And this comes back to the first point where we mentioned about the 3 pillars. You have the design, the components, and then the installation. The workers had no previous experience and they'd not received the manufacturer's internal training in how to do these up correctly. And my point that I mentioned a second ago about what do you consider to be a failure? Loose and broken bolts had been experienced on site prior to the accident, but they hadn't been reported. Now that's not because they were trying to hide anything, but it's because loose and broken bolts, it wasn't appreciated why they were becoming loose or why they were breaking. So if a bolt was loosened, they tightened it. If a bolt was broke, they replaced it. And they didn't investigate whether there were any more serious issues underfoot. And this is basically what is really happening. So you have a minimum load to maintain bolt integrity, and you have a maximum load at which point you'll start to damage something. So you want it as high as possible because you know that whatever system you use, there's going to be some level of joint relaxation after you've finished. So you go as high as possible without causing any damage. But the problem is, because the engineer has designed these in a way that's engineering efficiency, they've minimized the safety factor as far as they can. So sometimes that tightening inaccuracy can be the plus or minus 30% we've spoken about with the torque wrenches. It'll be too high, so that even though you've targeted a load that's in the safe range, you might start yielding the bolts, as we've spoken about before. And then obviously the other side to that is if you slide that down, so you choose a slightly lower target, you get into the self-loosening range. So you tighten that bolt up, you walk away, and then you start to get some sort of relaxation within the joint. And now suddenly bolts that were correct have moved into the self-loosening zone or the fatigue zone. They've dropped below their minimum required bolt load to maintain joint integrity. So by using some sort of technology tension control, plus or minus 5% is about the accuracy that you could expect out of these methods. So you can pick a very high load knowing that you're not going to go into the destructive zone, and then following relaxation, you know you've still got a large safety zone before you start hitting the danger. So looking at the RotaBolt product very quickly, what we've got is, we showed this picture earlier. So you have a bolt with a hole drilled through the center and the pin is fixed at the bottom end. There's an air gap, and this we mentioned about the difference between the 2 datum points. There's a datum point on the bottom of the rotor and a datum point on the top of the bolt. And that air gap is a known calibrated gap, the difference between the unloaded and the loaded condition. So as the bolt is stretched, that pin is drawn inwards as it stretches, and the air gap is closed and the cap locks. So the protective cap on the outside, in its unloaded condition or in a load state that's lower than the calibrated set, that cap at the top rotates freely. Once that air gap has been closed, you've got a locked cap and you can check quickly. And there is a video that'll be able to do that, to show that a lot better than I'm describing it. Every bolt is load test calibrated. So this means that every one you get has been tested. There's no batch testing or reliance on similarity materials. It's simple. With your thumb and your finger, you try and rotate the cap on the top. Does it move? No, therefore it's locked and you've got the correct load. If it does move, you haven't. It's quick, it takes a couple of seconds. There's no tools required, just a thumb and forefinger check. Low skill and it's very accurate. So you don't need huge amounts of training. If I put one of these in front of you now, you could probably use it based on what I've just told you. And it's accurate. So again, plus or minus 5% will allow you to do the checks as we've described in the graphs a second ago. It's repeatable. Provided you stay within the elastic range, you can load it and unload it as many times as you like. An in-service check as well. So it's not something you need to take any equipment offline to check. You just have a look in place. So how does that product give you the joint integrity assurance? Well, we've said about the mechanical strain gauge allowing you to measure the actual load in the bolt, irrespective of any sort of friction factors or any variances in that way. It directly measures that load in the bolt. So we do it in a couple of ways. So the tactile indication that I described in that quick example there in the cut through. So we indicate that a minimum load has been achieved, and that's the RotaBolt 1. There's a tactile indication of whether the fastener has achieved either of two set loads. So this is where you start looking at the maximum and the minimum. And you can see from the drawing there, there's now two caps on the top instead of one. There's a visual indicator that the minimum load has been achieved, and this is the RotaBolt Vision. So this is where the yellow line will be solid if you have the correct load, and then as soon as that falls outside of the calibrated range, it's sprung loaded to turn 90 degrees. So you can instantly see whether you've got the correct load in your bolts or not. So it's just a thumb and finger check. Yep, that cap is loose. And then it's locked. Simple. A bit of an anticlimactic video, that one, but I think it shows the point. And then we've got one step further, and I'm going to go quickly through this one at the moment. So we've developed a Bluetooth connected, remotely monitored bolt. So there's a Bluetooth cap on the head of the bolt that allows you to read what the bolt load is from a mobile phone as you're tightening. So the installer has his torque wrench on the bolt, and then his mobile phone in his hands telling him exactly what load he has there. Again, color coded. You can switch it to a percentage if you prefer, but really trying to make it as clear as possible. So when they're under pressure, there's no interpretation, there's no skill needed. They can just see quite clearly that that load has been achieved. And then when it's installed, it gives sample data over time. So it then has a 30-meter range to a Bluetooth hub, and it sends your load readings wirelessly to the hub that then is connected into whatever data system that you have, be it a SCADA system or some sort of data collection network. So it allows you to monitor your bolts without ever going to site. That's just a quick example there, and a good example of how bolts are not that interesting. Done correctly, that load will stay relatively flat over a relatively long period of time. So any sharp spikes in these is a bad thing. Following the initial relaxation, you want your load to be relatively consistent over time. So it allows you, this RotaBolt Connect allows you to log on from anywhere in the world then with a mobile phone or computer desktop. So tension control, reusable as long as you stay in the elastic limits of the products. You can check in service. There's not a lot of skill level required. You can increase your productivity, lower your installation and maintenance costs, instant checks of bolt loads in place, no tools required, and it gives you that peace of mind. Some of the applications I'm not going to read all these out. You can see these in the videos later, but some key ones. We do a lot of bearings on offshore cranes. So the slewing bearings on offshore cranes. They are lifting heavy equipment into very dangerous environments. So it's very important that that bearing is maintained correctly. And we do a lot of work offshore with that. Again, wind is going to be a huge one moving forward as turbines get bigger. The gearbox connections, the blade connections, all the stresses going through the bearings now are going to be huge. So there's all sorts of different applications within that industry. Subsea, so a lot of these, especially the mechanical strain gauge technologies, can go subsea. So there's all sorts of different applications. If you're in any of those specific industries, another big one is heat exchangers. So we haven't really touched on thermal differential expansion rates and how thermal cycling can affect your bolt loads. That is a huge topic in itself, so we haven't really had time today in order to do that, but that's something that we can look at in future if anyone's interested in contacting us. And I'm just going to leave you with one final fact. Northwind offshore wind farm, 5 meter diameter flanges, an MPTP joint with M72 bolts. So we use the RotaBolt 2 system in order to control the uniformity of the clamp load. So when they walked away from this, they knew everything was done correctly. I mentioned earlier, their methodology was tighten every bolt, and then after 6 months, they'd come back and they'd retighten them all. Now, you imagine how long it takes to tighten 128 M72 bolts. By using the RotaBolt system, they came back and they used the cap to check which ones actually needed tightening, and only 4% of them did. Because they'd achieved the consistent clamp load at the beginning, they'd minimized the relaxation losses over time. So when they come back 6 months later, only 4% of the bolts needed to be retightened. So they instantly cut out 96% of their maintenance time. And so that's probably quite a good point to leave you with. My details are on the screen at the moment and can be circulated after this. So we're back to questions. And Matthew, you might have to help me with this because I don't know where they've gone.
That's quite all right. Can you not see the chat currently then?
Right. Oh, yes, I can now. I've got them back.
Got it. Okay, brilliant. Yep. I'll leave you to it.
No, right. Okay. I haven't been watching these as they come in, so bear with me a second. Main causes of relaxation post torque up. This sort of goes back to the first slide. I wonder if can you guys still see the presentation screen if I wind it back to?
Yep, we can still see the PowerPoint slides.
So it almost comes back to this. So what are the main causes of relaxation? So when you consider the joint, you've got the bolt, you've got the flange, and I can't tell what industry you're from there, but especially if you put a gasket in the middle of there, I mean, gaskets are designed to compress as you load them up. So that and the elasticity of the material, I think that's the problem sometimes, is that people forget that although these are metals, there's an elasticity to them. And that is where relaxation comes in, because the metals flex and the gaskets flex and the threads of the internal of the nut will flex and the threads on the external of the bolt or the nut will flex. And all these movements put together means that once you've torqued it up and you walk away, all that is still bedding in. You can try to remove some of it by, obviously, when you torque up, you do maybe a 33% pass and a 66% pass and then a 100% pass, but there's still that relaxation, and it's just the mechanical components settling into each other and the microscopic movements. And hopefully that's answered the question there. Right, okay. Scott Charlton, are the RotaBolt fasteners set up for single torque load application only, or can the gap be set for different loads? Okay, so RotaBolt set the calibrated gap during the manufacturing process. So you would tell us what load is required, and then we would calibrate it for that. Obviously, the RotaBolt 2, you can have 2 calibrated loads, and they can be recalibrated if they're sent back to us. But yes, effectively they're set for and I don't want to be offensive or anything, but there's a quite a good example there. Are the RotaBolt fasteners set up for single torque load? There's a ambiguity between torque and load, and people often mix those two terminologies up, so you've got to be careful. But yeah, the reality is it's a calibrated load set at manufacture. Right, so James Lowe, what is the capability of the RotaBolt solution in more extreme environments? For example, are the Bluetooth capabilities robust in high temperature or high humidity? Okay, RotaBolt as a whole, RotaBolt 1 and 2, we've got them in high temperature. We use them a lot for heat exchangers, where there's obviously a lot of thermal cycling, 500 degrees and more. We've had LNG and cryogenic, and we do subsea. So specifically with the RotaBolt 1 and 2, that's obviously more robust because they're all solid mechanical components. The Bluetooth capabilities, high temperature, short answer is no. You're talking 85 degrees realistically as a maximum, mostly because of the battery. High humidity, yes, the Bolt has an IP67 rating, and at the moment we've got the hub with an IP65 rating, so no issues with humidity, although Bluetooth as a technology doesn't work underwater, so it can be splashed, it just can't be submersed. Hopefully that answers that question. How do you take into account dynamic loads in a bolt? Right. That is where you work with the design engineer of the piece of equipment. And so, sorry, James Jackson, how do you take into account dynamic loadings on bolts? Most calculations generally refer to static load cases. We don't do that. That is for the designer of the equipment to do and to specify. So whoever makes the equipment will be taking into account those dynamic loads, and they will specify a calibrated load on installation that will compensate for those dynamic loads. So for example, a heat exchanger manufacturer will tell what load is needed at ambient temperatures in order to accept thermal expansion into higher temperatures. So you're obviously installing these bolts at an ambient or static condition. That is where the design load comes in order to compensate for, be it movement or temperature. Feel free, if I haven't answered that question quite how you answered, but feel free to put another question in the chat. Robert Harris, do you have any preload measurement capabilities for torque to yield joints? How many preload measurement capabilities for torque to yield joints? I appreciate what you covered today was only for the bolts in the elastic range. Yeah. The problem when you go outside of the elastic range is that calibrated gap changes. So we stay within the elastic range of the bolts in order to once you start going outside of the elastic range, the amount it stretches per unit of load applied starts to become a little less linear. So the gap is calibrated within the elastic range. It'd be interesting to know, in my experience, going to yield tightening tends to be a method of controlling the load in itself. So it might be that yield tightening isn't necessarily needed if you have some other sort of tension control. Do you have a magic value for maximum allowable relaxation, i.e. has to stay above 75% of target preload? Um, the short answer, unfortunately, is no, because it depends so much on the application. I say we've done cranes, we've done heat exchangers, we've done wind turbines, and they all have slightly different application needs. And the other thing you have to bear in mind as well is a carbon steel bolt will have a different elastic range to a stainless steel bolt. So a carbon steel bolt, you might go to 80, 85, possibly even 90% of yield during tightening. With a stainless steel, you wouldn't do that because its properties flatten off a lot quicker, and you'd only really get to somewhere around 55% of the yield before you start getting into the plastic range. So unfortunately, no. Okay, I don't see any more questions in the chat there. Have you got anything come through, Matthew, on your end, or are you just looking at the same thing as me?
I'm just looking at, I assume the same thing. So
Okay.
I guess that'll be the end of the questions, which finishes off nicely. So unless any more kind of come through, thank you very much for that, Craig. That was a great walkthrough on the theory of bolt tensioning, also kind of the importance and honestly the extraordinary results I personally found for the safety, time and cost through load measurement. I know as a young engineer, I kind of very much like to hope to see some of this technology in industry more going forward, especially the IoT related devices such as the Kinect. That's particularly interesting, to me at least. Oh, we have one kind of final question to finish us off.
Oh, right, okay. Any indication on cost difference to a standard fastener? More is the short answer. It's very difficult because it depends on which. I'm assuming you're talking specifically about the RotaBolt. It varies based on size, on material, on quantity. It varies on so many different things. It can be 25% more. It can be 150% more. It really depends on lots and lots of different variations. The one thing I will say is it almost always pays for itself really quickly with the cost savings in maintenance and lost product and things like that. So, and I'll put that, I'll be honest, for the RotaBolt product and any sort of tension monitoring, I'll widen that out, is you're introducing a level of control to where there previously probably wasn't any. So you're going to get benefits whichever you choose. Oh, we have another question coming in. Nick Latham, would it be correct to assume that the Bluetooth version is not ATEX rated for explosive environments? Yes, it would be correct to assume that. It's a very low powered piece of equipment, and we believe that it would pass ATEX testing and that we could rate it for ATEX zones. As a new product out, and as primarily things like offshore wind and industry was the driver behind it, ATEX wasn't something that we went for. So if the market demands it, we'll do it. But the shorter answer is no, it's not ATEX rated.
Brilliant. So I say that brings to an end this afternoon's talk, probably. I know you did have your email up before.
Oh, I did, didn't I?
Craig,
Yes.
if you wouldn't mind. I'm sure you wouldn't mind if anybody has any more specific questions about the RotaBolt product. They could reach out to you over that. So we'll just put that back up at the end.
To flick through. Right. There we go. I'm better at bolting than I am at presentation. So
anybody can note that down if they want to know any more. So once again, I'd like to thank Craig for joining us this afternoon and giving up your lunchtime to share with us the technology from James Walker that we're working on through RotaBolt. And again, thank you very much, everyone, for joining us this afternoon, and I hope to see you on future events. Thank you very much.